Hello, so we'll now be presenting about task 1 for our 2D project. So task 1, we are required to come up with a multiple linear regression model for death due to COVID-19. So first we imported our data set, which is the hour in data COVID death data set. So as you can see, there's a lot of missing values in this data set, but there's also a lot of countries. So we choose this data set as there's a wide range of uh, data points. So here are some of the columns in the data set. There's a lot of columns. So the first thing we had to do was to choose the features which we want to use. So in choosing the features, we did some research and we plotted some graphs to see how the different points correlate. So over here, and take a look at the plot for total tests against total deaths show actually like a somewhat linear relationship. Similarly for the time, which is the number of days since 1st January 2020, as well as for the total number of cases. So based on our preliminary analysis, we actually chose these three factors to use to train our multiple linear regression model. So first step we did was to actually read in the clean CSV, which we cleaned up earlier, by removing the missing data points and selecting the columns that we're interested in. Then we extracted the features and target. So these are the cleaned up data sets. Then we proceeded to train by using a gradient descent algorithm. And as you can see, this is the cost function. And then following which, we actually plotted some graphs to see whether the prediction is similar to the initial values, the dataset values. So based on our preliminary analysis for the three factors, we found that the adjusted R-square value is about 0.88, so it's actually quite good. But we wanted to determine like whether it's the best for the combination of these three factors. So we actually created a function to find all the different combinations, and when we tested, we realized the one with three factors, as you can see here, is actually still the highest. In part 2, we are focusing on how is it safe for a particular individual with COVID-19 to recover at home. This question came up as the Singapore government announced that they want to make home-based recovery the default. So you may be asking, how do we define whether it's safe for one to recover at home? We define safe to recover at home as one not needing to be admitted to ICU and not dying. So based on these two criteria, we determine based on past data whether an individual will have been safe to recover at home or not. We chose our data set providing the data on individual patients in Mexico, and we cleaned the data. The first step we did was to actually find the translations for each value as well as the description for each column. And in processing our data, the first thing we did was to rename the columns for easier reference. We also changed the values from 1 to 2, which represents yes and no, to 0 and 1, no and yes, which is something we're more familiar with. Next, we process the data, taking a look at the death date of the person as well as whether they require ICU in order to create our target feature, our target column, which is safe. So this column safe actually will determine whether one is safe to recover at home from COVID-19 or not. We also plot some plots in order to help us decide which features we would like to choose in our logistic regression. So here are some of the plots. These plots help us to choose as we are able to see which columns actually have a lot of missing data and which columns have disproportionate amount of data. For example, in pregnancy, we see that there are a lot of 97, which is actually unknown data. For values such as asthma, we can see that there's a disproportionate amount of data in the 0. So following analysis, we actually chose certain features such as male, age, diabetic, hypertension, and obesity, and our target column is safe. So here are some helper functions. In order to start training, the first thing we did was to split our data set into train and test. So we split 70% for training and 30% for testing. We also use a random state to ensure that the results is reproducible and we will not get a random result every time we run the training. So we also decided to normalize the age using max min normalization, as that will allow the range of values to fall between 0 and 1, which is similar to the other columns, which are binary values. And this is a classification model. We make use of a logistic regression instead of a linear regression or multiple linear regression. Here are some helper functions to help us do our logistic regression. Here, we perform a stochastic gradient descent, as after research, we found that a stochastic gradient descent will actually perform faster and better compared to a normal gradient descent. In evaluating our model, we made use of precision, as we wanted to be very sure of our prediction, as should the model predict falsely, it could actually lead to a life and death situation. In our initial testing, we actually obtained a precision value of 0.52 for the test set and about 0.53 for the training set. Following which, we discussed and decided how to improve the model. So, as with many machine learning tasks, more data will definitely help. As our current data set is only focused on Mexico, we might not be able to get representative data of people all around the world. Secondly, as this is a classification task with binary variables, it is good practice to ensure that the training set has approximately equal proportion of two classes. However, as you can see from here, our target value of 1 actually takes up about 0.3 of the total count for our target values, which is about 30% only. Hence, in order to alleviate the issue, we actually randomly pick the rows with target value 1 to match the proportion of that with target value 0. So with this improvement, we actually managed to get a better precision score of 0.67. However, with this score of 0.67, it's still not sufficient to be deployed as a model for use, as it's a very low precision to be used for something with regards to life and death. Furthermore, if we take a look at the beta values, it is actually counterintuitive, as it seems to suggest that being older will actually allow you to be safer and stay at home, and that applies for having diabetes, hypertension, and obesity, as the value of Z increases with all these constants. You seem to head more towards 1, which is actually indicating that it's safer to stay at home. This is very counterintuitive, and when we analyze the data, it actually seems to suggest that the mean age of people who are safe to stay at home is actually higher than that of the mean age of people who decide not to stay at home. So it might be due to the data being skewed or not accurate. Our hypothesis that people who are safe to stay at home should be those who are not in ICU or not die might actually be wrong. We're now presenting the bonus part for 2D, which is the interactive website. So we'll run it from Vocarium. Firstly, we will go into the repository. Then we will activate the virtual environment. Then we will run the Flask script. So after Flask is running, we'll go to myserver.vocarium.com. And this is the interactive website which will question normal people on like their current status, and they will find out the results of whether it's safe for them to stay at home. So we'll answer the question whether you're male or female, and you can enter your age. This will check for the input, as it can't be negative and it can't be too big. For example, if we enter 180, so we assume that the maximum age will be about 150, which will be reasonable. So let's assume we are 55 years old. We are not diabetic, and we do not have hypertension, and we are not obese. So after performing the calculation, we will actually give a recommendation based on our logistic regression earlier. So based on the code, we can actually see that all these calculations is done here in routes.py. So after the form is submitted, which will actually call the function getResult. This function getResult actually makes use of the beta values which we found earlier using our logistic regression, as well as normalizing the age. So yeah, these are the other functions that we will use when calculating. So based on that, the user will be able to see their responses as well as the recommendation given to them. Yep. With that, we come to the end of our presentation, and we hope you enjoy it.